battery power. Oh, something's on. I have no idea what's on. Something's on. Okay, I think that's this thing. Well, let's log in here. And if this, okay, that does that.
Is that black border? That might be. Is that black? Yeah, that is. Okay. All right. I have to enter the same information I just entered a minute ago. Semester. And dynamics, which is, for some reason on mine, it's on the top. I don't know why. Got here. Now, I think you get a different view maybe than I do. I don't know. Does your view look like that? Okay, so I mean, we can go through each one of them here. I don't know whether to wear my glasses or not. I tell you what, this screen doesn't do a great job. I have tried my best to kind of get it lined up, and I don't know. They used to have software. Let's see. Let's see if I can. Oh gosh. Let me just try settings for a second. Okay. They don't even have. You know. I guess we'll just go with what it is. So all you have to do is just go through them. Let's see. He's got difficulty rankings, and I don't know how accurate those are. So I mean, you just go through them. Let's see. I'm not sure if you're seeing. Yeah, I guess you see the whole view. I don't know. So for some reason, part of this is not showing on my screen here. But I guess it is showing on this screen. It says, answered the, okay, initially the car travels on a straight line with V as shown in dot. But, so what he has is, I've noticed this on all of them, there's a little darker area in which it's the text, and sometimes the stuff is missing. And then you look down here and it's a better write-up. So if the brakes were applied and the speed of the car is reduced to V in T seconds, determine the constant deceleration of the car. So that's kind of a difficult thing to understand. But then when you go down, it's like the thing in dark. It's always kind of repeated. I'm not exactly sure why they have it that way. But it says initially the car is traveling in a straight line at 37. Maybe I will bring up the thing and write on the board. It says it's initially going at 37. Because you can't really see very well. So it's initially going at. And obviously, the stuff in the little dark, if you look down, you'll see it rewritten. So it's very strange there. So I would say just read this to kind of get a feel, and then read this to get the complete. So if the brakes are applied, and the speed of the car is reduced to, and notice he said he has a little blank in 17 seconds. If you look up here, it's shown in, okay, reduced to V in T seconds, determine the constant deceleration. So if you read this first, it's very confusing. But then if you get down here, after you get past this initial like description, it'll restate the same thing, but it has all the information. So don't get confused by this little dark thing. Just read it to kind of get a feel, and then go on down from there. Then it says, determine the constant deceleration of the car. So, I mean, if you just went through the equations, then the acceleration, which would have to be a constant, t squared over 2. But you could also write down, and that's acceleration constant. So those are the two equations, although they usually list this one above that one. And then they'll say acceleration is equal to acceleration constant. So you know you got acceleration, velocity, and position, or whichever. So he's telling us this. He's telling us this is 37. Determine the constant deceleration of the car. Okay, if applied to the speed of the car is reduced to 10 meters per second in 17 seconds. So if you look at this thing, it's obvious that he's giving you the fact that velocity as a function of time is equal to 37 plus ACT. Well, that's 17 seconds. This is 30 seconds. I'm sorry, 10. So you just get 10, 37 plus AC, and 17. You just solve for AC. Now, on mine, he has the answers, but if you look at this, that's, again, so that notation, usually that's a V with a sub instead of a 0. So I don't know why he doesn't have the V sub 0. But that's the same thing, acceleration times t. And then you move that to the other side, so it's just basically, that. I mean, so all these problems are fairly not that difficult. The thing that's distracting, I think, is the darkened thing that says description. You almost could ignore it and just start reading down here. Or just read it and say, what? And then start reading down here. And then it starts making sense because the words get repeated. It's obvious that, so his description, initially the car travels on a straight line with the speed of V0 as shown in, but he replaces the V0 with that. And then he doesn't, well, he does say part A, but up here he says A. If the brakes are applied, A. If the brakes are applied, the speed of the car is reduced to apply. If the brakes are applied, the speed of the car is reduced to. So he repeats himself. There may be a reason for that. This is probably some sort of thing that has to do with programming. So somebody, obviously it's a web page, so there's a program behind it. So this may have been in there with variable sets, and the description was written completely, and then the code went through and replaced the V0, replaced this, replaced that, and wrote the rest of it and gave you the picture. So there's probably a database there with all this set up that way. So don't get too distracted by that part. And then let's see. Okay, so I can hit this button, go to the next one. You'll see the same thing here. The same thing in regard to his little verbiage. In other words, he starts with his description. A particle moves along a straight line with an acceleration of. This time he attempted to put it in there, but if you look at it, it looks very funny here. And again, this is probably due with the software, with the fact that it's a program. This is programmed interface. Or T is in seconds, but T is a particle. But you even notice the fonts are different. All of the makeup of the font. This is trying to write it out in just regular text, and this is a mathematical typeset text. So all of it appears that way. This one appears to be, the other thing, it looks like it says to the left of, and then dot, dot, dot. So I don't know the true justification why it's there. And it says the particle moves on a straight line now. Okay, so, you know, A is equal to 4t squared minus 2. And it says determine the position of the particle when t is equal to, I believe that says 4 seconds. But you know, if you want to go to velocity and you know we want to go to position, you've got to, okay, so here I'm going to do a double line over here. dv dt is equal to acceleration, and as a result, dv is just equal to the interval of acceleration dt. And that would be from t1, v at t1, t, and I'll say v at t. And so, then your question is, when t is equal to located 4 meters to the left, so you got to go through this a couple times. Okay, so let's take straight line acceleration. When t is equal to 1, I'm sorry, t is equal to 0. Just go ahead and replace that. It's located 4 meters, and when t is equal to 2, it's at 20 meters to the left of the ocean. So it looks to me like what you're going to have to do is you're going to have to do this. V at T2 and V at T1. You're going to have to take this. Well, I had it written right there. Put it in here and integrate it. And T squared minus 2 dt out of this, you're going to get a cubic, like whatever the value of. You're going to get a t to the third term. You're going to get, you won't get a t squared because there's no t, but you're going to get a t out of here, plus an integration constant. And then you're going to have velocity as a function of a polynomial with the t third, t, and a constant. And then you're going to integrate it again. ds dt is equal to v, and as a result, that. So you take that equation and put it in here, integrate it again. And I don't know what that is. That's like a little image or something. I don't know what that is. But express your answers in 3 significant digits. What is the view available helps? Hints, I'm sorry. Okay, I don't know where my mouse is. Okay, hint 1. Hint 1, where'd it go? Oh, it's in the blue. It says, you're given a particle's acceleration function. Recall that instantaneous is defined as the second derivative position. Well, it is, but I did it twice. I did an integration, and then I did an integration. Use this to find the particle's position. Okay, that may be true, but I did it once to get to the velocity, and then another time to get down there. So the hint probably could have said something better, like, I don't know, since the acceleration is there, that's true. It could have broken that into 2 differentials there. Okay, 3. Okay, here we go again. It has a, oh no, okay, here's the picture on the right. Here's the equation. if you notice, okay, so again, he's typeset stuff, so the description, position is blah, and in there's nothing down there, but this and this are the same. So just be aware, when you're reading the thing that's in the dark, it's repeated and expanded upon. So again, I'm not sure what the purpose there. Okay, so it says the time, wait, determine the time which velocity, when the velocity of the particle is zero, and determine the total distance traveled by the particle when t is equal to, and I can't see that. Oh, it just has a pound sign. So that kind of, okay, so I'll need to go down to here. Pound, okay. View available hints. See what he has for hints there. Does he hint and tell us what the time number is? Okay, the position of the particle, where t is in seconds. That's great. Part A. Determine the time when the velocity of the particle is zero. Okay, that's part A. Part B, oh, okay. All right, so he's determined the total distance. So this is the part when t is equal to 2.3 some seconds. So again, if you just look at the thing, this time I have a quadratic. So you just ds dt equal to the velocity. Well, if you look at it, take the derivative of this, that squared, that's a 4.00, I think. So 2 times 4 is 8. And if you were a programmer, you would put the zeros. I mean, minus 12. Did he want to know, determine the time when the velocity of the particle is zero? Well, if you put in t is equal to 12 eighths, then multiply that times 12, you get 12 and you get nothing. So, however, there's no guarantee that you would get exactly 4 here. So when he's saying 3 significant digits, figures, that's probably why he has those other decimal spots there. And in his hints, he probably says, the hint is just, is that the hint? Where's the hint? Wait, view available hints. Oh, there's the hint. Okay. So the hint, instantaneous velocity is determined the derivative position. So that, derive the expression for the velocity, equate it to 0, and find the corresponding time value. So that's all you're doing. So you just kind of go through them. Use the hints when you can. And then the answer to the second one, let me just go and try to find the mouse and look at the hints there. Determine the total distance traveled when t is equal to whatever. For me, I would kind of look at this thing. Okay, I lost track of the equation, but I think it was s is equal to 4t squared minus 12t, or was it 12t? Plus 6. Plus 6. To me, what I would do, I don't know which way you want to do it, you could do it s as a function of time. And you put in t is equal to 0, and you get something that lays down here. Okay, s is equal to 6. Now put in t is equal to 0, I get 6. So I don't know how to do this by scale. But anyway, you're going to get something that looks like that. It could have, what I would try to do is use MATLAB and plot it. The thing is you're not going to have this, because that's a third order. You're going to have, so the number of axes crossings is the order, is a general rule. So you might have something like that, or it might be over here. So the key is, do you start here, go down, and back up? So, in other words, if you look at the plot, let's just take one of the instances. Let's say it's just stuck out here. If you start here at some location, and you travel to here, then that's the distance traveled. However, if you're starting here, you travel this direction, and then turn around and travel back the other direction, you might think the total distance traveled was that, but it's actually this, and then back up to there. So your particle may actually start somewhere, go out somewhere, and then return back a little bit. So what he does is to determine the total distance at this weird time here, it's necessary to investigate the path. Consider a graph of the velocity function. Note that the particle is traveling to the left when the velocity is negative, and to the right when it's positive. Also, v is equal to 0 for t found in the previous part. So, what was the time? Okay, so in the last one, okay, so it's obvious that that's the case. So, it moves to a certain point, stops, and goes the other direction. So it does do this. So it travels along the path, stops, starts traveling back up the path. So to calculate the total distance, you determine the particle's position at t is equal to 0. T, that's supposed to be when the velocity is equal to 0. And then t at 2 things. Recall the distance is the length of the path over which the particle travels. So it could go a distance and turn and go back the other direction. So that's kind of a leading thing. It kind of leads you along there. Velocity of the particle. Okay, so this is another thing. The description is darkened, but on my screen over here, it looks like it's just a slight pinkish color compared to the other. So when you just see the description, I mean, you can glance at it real quick to get an idea, but it's very incomplete. And then he has the same thing written below it that's more specific. Velocity of the particle travels a straight line like that. Suppose s is equal to 0 when t is equal to 0. Determine the particle's deceleration when t is equal to whatever. And that just goes back to that. Okay, so you got this one. Now, it's kind of a tricky question, because if you're asking for a deceleration, you're assuming that it's negative. So the answer you may want is a positive, I don't know. We should take the derivative, and then he wanted to know it at 4.3 seconds. So let me look at the hint and see what he says there. Recall how the, two hints. Okay, recall how the velocity and acceleration are related, particularly the particle is slowing down, or the speed is increasing. If the particle is said to be decelerating, you may need to use differentiation. But you would need to use that anyway. But anyway, since he gave you the equation, I wouldn't even use it. I mean, I would just differentiate it. So I don't know. Instantaneous acceleration times t, the vector is found by taking the smaller and smaller values, so that. Okay. Well, if you look at it, I mean, you just take the derivative. So I don't know. This is kind of a, I don't know. It's kind of a strange hint. Okay, there's a part B, which says determine the particle's position. Okay, that's why you actually. So this is a situation where you are given a velocity as a function of time, and you are asked to find its acceleration. And so to get there, now you're asked the position. And so to get here, you go through this equation to get here. But to get this other one, the supporting equation is this. And so, as a result, this. Now, to get to there, you have to kind of do this. To get to this. So to go to one, you do the differentiation. To do the other, you do the integration. What he gave you on this is he gave you the initial position for t is equal to 0, and he's asking you to determine the particle's position at 4.3. So I don't remember what he said for the position. Oh, he said 0. So he said the initial position was 0. So what I'm saying is he said that. So just take the equation, put it in there, and integrate it, and you'll get the other one. And of course you put in your limits of 4.3, and then you're looking at your position at 4.3. So essentially this is nothing more than the position at 4.3 is equal to the integration of the velocity as a function of time integrated from 0 to 4.3, and you just put in the equation you just integrate it. That's all there is to it. So all of these are fairly simple. They just take, okay, so again, you got the thing where the particle moves a straight line, acceleration. Okay, again, he has that, but he defines the numbers here with the nice equation and everything. And, okay, that's interesting, where S is in meters. So this one, it does not, I do not see a hint on this one, but this one is the one that is the different frame of reference. Okay, I can't, I'll tell you what, I can make it bigger. Okay, part A. So, this one, okay, oh, here it is. Okay, this one is this, acceleration is, and this is just 3 over S. Now, at an initial thought process is, okay, then he says, the particle's curve with 3 is this. Determine the particle's velocity when S is equal to 7. So, this is that situation where you have that. So if you look at it, let me think about this. dV dt equals 2S. Now the problem is, I don't have that that way. So I'm going to scoot this to the right, or I'll write it, I'll flip them. A is equal to dV dt. However, ds dt. So this is the same as those two put together. Then I can rewrite it, instead of erasing, I'll do this, v dv ds. Now I can take the ds, move over and hit it against this. So, by looking at these two together, I can rewrite that equation acceleration is different under there. I can write acceleration ds is equal to v dv. And then I can start integrating things. And so I can say S0 in S. And I'll say B, how do I say it? At S0. And then I'll say B. This right-hand side is pretty simple. 1/2 B squared, oops. B squared evaluated from B. When, I should say at, I'll say when, that. And then this, so this is where you take that thing and inject it in there. Now, he should have told me, okay, the particle's velocity, when is released, okay, he wants to know that, released from rest, when, okay, so there's your key, when S is equal to 1. So when S is equal to 1, then it's released from rest. Meaning that. I mean, I could just copy that over right there. And then if I just insert that, that's just B. The whole thing on the right becomes 1/2 B squared. The thing on the left is you have to integrate that and put in S and 1 right there. And so you move all that around, and you can take this V, which is what he's asking for. You can multiply this left side times 2, and then take the square root of it, and that'll give you the answer. But the key is this one had to be, you had to use the, whatever that rule, to chain rule, whatever, to take the derivative here, which you didn't have velocity as a function of time, but now you do. You have it split, but you have a ds on the bottom, so you can bring it over and operate it against the acceleration. Okay, wait a minute. I can't find the mouse. Oh, there it is. Oh, it looks like it's a similar kind of thing. So it's the same kind of setup. It's just now the equation acceleration is a different function of s. And so, does this one have a hint? This one may not have a hint either, but it's the same thing. So it's just now you stick a different value in there. If it starts from rest when s is 1, okay, so it has the same thing. Just a different equation goes in there. And you want to know it at a different time. So instead of whatever that was last time, it's 2 this time. So that one becomes 2. This one? Oh, here it is. Okay. So each of these screens looks very different. Okay, so again, this one might look. Okay, so the particle is moving along a straight line with initial velocity of that. When it's subjected to an acceleration that kind of looks like this, when v is in meters per second, how far does it travel before it stops? Okay, so again, and I had a red marker in here one time, or someone had one. Oh, here we go. The markers are kind of going away. So you have this. V squared. No, v squared 1 over square root. Particles moving along a straight line with initial velocity, okay, V naught is equal to what? 8. When it's subjected to a deceleration that looks like that. So now, how do we go about that? Let's see. Determine how far it travels before it stops. So second thing is this one. This one is number 7. Okay. So when you look at these things, they look strange until you're kind of like, it's really bizarre. I mean, I probably shouldn't even have given you this one, but it's too late now. You have an equation that looks like that. Now the thing is, you've got this now on this side, and this now on that side. If you kind of imagine that this is not there, or maybe I'll just rewrite it. This time I could take this, move it over, and this and move it over. In other words, if I have that information, I can do this. I could leave the minus over there, or I could not. It's just kind of up to you. In other words, I could do that, where I left the minus 1.1 on the right side. But I could have just as easily brought it under here, but it's probably just as easy to leave it right there. So take this over here, take that over there. Now it looks like an integration. And now I can do that. So all you have to do is when you do these, you make sure the lower limit of each one is associated with each other, as well as the upper limit. You just, whatever's in there, you got to make sure it's the right thing. So this is dV, so this has to be a V at some time. And that time has this, whatever that V is, has to correspond to that, whatever that V is, has to correspond to that. So then the next thing is what corresponds to what. There's the initial velocity of A. Now, he didn't tell you when you can start and stop your clock, so I'm just going to say that and that. So that's associated with this, and this is associated with the initial velocity at time 0 A, subjected to acceleration like that. So now, I don't want to integrate that, but if I did, I could put in here in engineering sense, and out of this, all this junk, I could integrate and pop after some effort. I'll end up with the velocity on the, so I'll have some stuff on the left, I'll have some stuff on the right. What I may end up with is velocity as a function of time. It might not look happy because of this, and I don't feel like doing it, but it's not going to look happy, but it doesn't matter. That's what you're going to end up with. And then he said, okay, how far does it travel before it stops? So at that particular point, I would come in and say, well, it stops when V is equal to 0. So what time is that? And then solve for that. And then the next thing is, well, unfortunately, to get to here, I got to do this. Okay, so dS dt is equal to V. So unfortunately, integrate dx equal to the integral of dt, where whatever that was got stuck in there. Okay, velocity, okay. Okay, so here, let me move this up a little bit. This is the way. So, velocity, it stopped when it was there. What time is that? So it starts here. What time is that? Okay, that is that time right there. And did he start? Did he say how far? How far does it travel before it stops? So that would be how you would do that. You would find, figure out what time it was. Stick it in here. Turn around and do these intervals. Now, this might not be a happy equation. A bunch of stuff with some t's in it might be, who knows what it is, you're taking the integration bit. You put it in here, you integrate again, put that time that you found on the velocity stop in there. That'll give you on the right-hand side a number. On the left-hand side, you're just going to get S, because this is time is equal to 0. You're going to assume it starts at that position, and that's pretty much it. Okay, this one, okay, wait, let's go back one. Okay, let's go forward one. Okay. So there's the description, and then the description under it. Okay. So it just says 2 cars. Do they have constant deceleration? Both persons have 70 miles per hour. Okay, at that. Okay, all right. So you have to. So you look at this thing. Decelerates at 8 feet per second. So this car is this A? No, this is B. Traveling at 60. Driver B suddenly implies causing his car B to decelerate 8 feet second squared. This is B per second. And then A, it takes the driver of the car A 0.7, okay, let's say delta T is equal to 0.75. This is the normal reaction. Okay, I'm going to pause it right. It decelerates at 17. So he's decelerating at 17. So he's pushing his brakes really hard. Okay. That's great, but what's the question? Okay. So let's make sure I got that. Okay, B is traveling distance. Both cars. Oh, both cars are traveling at 60. He decelerates at that. Now, unfortunately, I did all that. I know what I could do. Here's car A. Here's the distance. And here's car B. Because I'm going to scroll the screen up in a second. I don't know what that is. Maybe that's a guy's name. So then you scroll down. Minimum distance so the cars avoid the collision. So on this is not that difficult. So what you would have is SA is A naught plus BA. So plus acceleration of A T squared over 2. Acceleration of B T squared over 2. So what you could do, okay, I think I could basically start a timer at the minute they hit their brakes, or the minute that B hit its brakes. So B hit its brakes. It took this amount of time for this guy to recognize that. So I would say I have 2 times T1, which would be associated when B hit its brakes, and T2 is when A hit its brakes. Oh, okay. And T2 minus T1 is equal to 0.75. I think we got to go for a second. And this got me in seconds. So, at T1 to T2. Okay, so let's say this. Acceleration A from T1 to T2. Acceleration A being this guy is equal to 0. Acceleration B, well, I got my T faced that way, I'm going to do that, is equal to minus 8. So what you do is you enter this, and then you got another set of equations where this is T2, let me move it, it's kind of getting clumpy right there. So when T is greater than equal to T2, the acceleration A is equal to minus 17. So what you have is two specific times, T1 and T2. What you really, I mean, you can look at after T2, but what you want to look at is to make sure during that 0.75 seconds, after he hit his brakes, this guy didn't hit him before he put on his brakes. So in fact, since this guy's moving at the same speed, and this guy's decelerating more than this guy, you're really only looking for at T2. In other words, T1 is when he hits his brake. By the time you get to T2, you can rest assured that anytime greater than T2, you're probably going to be okay. So you go through there and you basically figure out the positions during all that, and then you figure out the subtract the two, and that would be the distance. So, okay, what's 9? Oh, it had hint. That one had hints. Okay, so this is a straight up equation of time. And so that's just differentiation or integration. This is has hints. Oh, why did I do this one? Here, I'll grant full credit no matter what when you get to that one. I shouldn't have given you that one, because that has a, yeah, if you want to do it, I'll give you extra credit for it. How about that? Oh, and this one has a video. Oh, this is a, what's it called? A coaching activity where you just kind of watch the video and answer some questions. Let me see if the video does work, though. Oh, it does. Okay. Now what do I do? Okay, I guess. So these last two are just video solutions. So they're basically, it's just a watch and answer a multiple choice question. The average is infinity. That can't be. How can the average be infinity? I don't know. So just go through there and do those. Those are due by Sunday night. Just oh, that screen is still up. Okay. And I never resolved the issue with the projector there, but it's okay. Oh, I had the display on the whole time. Eh, well.